Hello, today we are going to do a question on the data function itself, and that question was asked in TA for examination 2014. And so here is the question that I'm going to soon share. And we already know that we've done a lot amount of questions, around 2 to 3 questions on 2 to 3 sort of problems on the data function, the data potential itself. And so here is the problem. So what does the problem? This particular problem was asked in TFR, and let me just the problem so that everybody can see it. So this is the problem that we are going to do. So what does problem say? Problem says is, what does problem say? That if particle was initially confined in, so particle was initially confined in one-dimensional, confined in one-dimensional well. So initially it was confined in one-dimensional well. One-dimensional infinite potential well, sorry, infinite potential well. So initially it was confined in one-dimensional infinite potential well. Of length L it is given. So initially it was confined in a one-dimensional potential, the particle of mass m, or I think it's not given, mass is not given. Overall, it looks as if it is a one-dimensional potential well. Okay, and in this one-dimensional potential well, what happens is if a vanishingly thin. So what does this line mean? Vanishingly thin. Vanishingly thin, but strong repulsive. Okay, so what does this particular line means? So if a vanishingly thin but strong repulsive partition is introduced in the exact center of the box. Okay, so what does it mean? So you've already studied Dirac delta function, you've already studied Dirac delta potential. So it suggests that this vanishingly thin means and strong means what? It means that there is a strong repulsive Dirac delta potential which is acting at the center of the box, because it suggests, the line suggests that this is a vanishingly thin. So it is a vanishingly thin and but strong repulsive partition. Okay, so this is partition means it implies that there is some strong repulsive potential which is introduced at the center of the infinite one-dimensional potential well. Okay, so this is how it is. Sorry. So here it is. So initial state was initially your particle was confined in a, so this is your initial state. So I'll write this is my initial state. So initially my particle was confined in one-dimensional potential well. And then what happened was, next what happened is, it says that a vanishingly thin but strong repulsive partition is introduced at the exact center of the box. So at exactly the center, a strong repulsive Dirac delta potential sort of potential is introduced, and this is 0 and this is L. Okay, this is one more thing. And the particle is allowed to come to its ground state, then the probability density of finding the particle will appear. So this is what I was telling, that in examination, not much like whatever we were doing like energies and everything we were doing. But in examination, you are not left with much scope. So in examination, most often they would ask you the plots, like wave function. That is why I constructed all those plots in the Dirac delta potential also. Okay. So how to go about this problem? So now here you do not have an attractive Dirac delta potential. Here you have a repulsive Dirac delta potential. And the questions in this particular question is asked is, how would your psi x ka mod ka whole square versus x look like? So this is what it is being asked. So it is asked that how does psi x mod ka whole square versus x look like? Okay, so this is how it is. Okay, now how to go about this problem? So what I would do is, see, I know that initially I can say that my wave function, eigenwave function, was under root of 2 over L sine of n pi x over L, and energy state in general is given by n square pi square h cut square upon y is ml square for one-dimensional potential, one-dimensional infinite potential. infinite potential well. Okay. So for one-dimensional infinite potential well, your energy is given by n square pi square h ket square upon twice ml square. Now, if at all, okay, sorry. And it is said that particle is allowed to be in the ground state. So what would be the ground state? So your ground state would be root over 2 upon L, and then I can write sine of pi x over L. And then I can write here that your energy of ground state would be equals to, I think, pi square. You can have h ket square, and then you can have 2 ml square, right? So these are your ground state energies as well as eigenfunctions. Okay, so this is how it is. Now, if at all a repulsive, strong repulsive Dirac delta potential is acting at the center, obviously there would be some change in the energy and there would be some change in the this wave function, and this is what we are trying to figure out. So what would be the now how would the differential equation be written? Minus h ket square upon twice m. This will be d square psi upon dx square. Here it will be, I think, v naught Dirac of x minus L by 2, and then there would be psi, and here it will be E psi. And remember, now we are in one-dimensional potential well, where energy is given by n square pi square h ket square upon twice ml square. So overall, this energy is positive. Okay, so initially we were taking an attracted Dirac delta potential that your energy should be negative for particle to remain bound, but in one-dimensional potential well, despite your energy even being positive, your particle remains confined in the well because the potential outside is infinite. So it remains confined in the well with the energy given by n square pi square x square upon twice ml square. Okay, so now what will happen is, let us solve this particular differential equation. So this will be like d square psi upon dx square. You will have some 2m upon h ket square. Then you will have, I think, E minus of V naught Dirac of x minus L by 2. And then I think you should write psi here and you should write 0. Okay. Now you already know that this is a one-dimensional potential, infinite potential well. So your psi L and psi 0 should be equal to 0. Why? Because outside this, beyond 0, like to the left of 0, your potential is infinite. And to the right of x equal to L, again, your potential is infinite. So if potential is infinite, then your wave function should be 0 at these or these. And by continuity of the wave function, your psi 0 must be 0 and your psi L must also be 0. So d square psi upon dx square plus 2m h ket square E minus V naught Dirac of x minus L by 2 psi is equal to 0 with boundary conditions that I'm writing. First boundary condition with this. Second boundary condition, even if your what should I say? Even if your Dirac delta potential is introduced at the center, but overall the wave function should remain continuous inside also. So what I would write, even if this is introduced, it should not change the continuity of the wave function. So I can write psi of L by 2 plus should be equals to psi of L by 2 minus. Okay. So in any case, your wave function should remain. Your wave function should remain. You can say continuous only. So these are continuity conditions at the boundary. So this is continuity condition at 0 and L, which form the boundary of the one-dimensional potential well. And this is the continuity condition at the center of the well where your Dirac delta potential is introduced. So even if the Dirac delta potential is introduced, your continuity condition should not be violated. The third condition, as we all know, how do we derive that third condition? We know that we integrate this expression from a point around which at a point around the point where your Dirac delta potential is located. So your Dirac delta potential is located exactly at x equals to L by 2. So if I use that thing, so if I integrate my above differential equations, from L by 2 minus epsilon to L by 2 plus epsilon, what I would get simply d psi over dx. And this will be, I think, L by 2 minus epsilon to L by 2 plus epsilon. Then you will have this 2me, you forget about it. This particular thing will become 2m. I think this will become, I should write minus also. Minus 2m v naught h ket square, and then it will become psi of L by 2 is equal to 0. And also this particular differential equation we'll see later on, but overall understand this point. So this will become d psi upon dx. Now at first, before doing this, we should first write what will be the psi. So as we know that we cannot solve this particular differential equation for x equals 12 by 2. So what we'll do, we'll try to solve it for x not equals 12 by 2. So if your x is not equals to L by 2, then your Dirac of x minus L by 2 would be, I think, 0. And if it is 0, then I should write my d square psi upon dx square plus you write this particular, once I will write the entire equation. So this 2m upon h ket 2m h ket square e, I would write, let's say, k square. And this particular thing I'm writing alpha, Dirac of, once I'm writing, then I'll use the entire thing. So this is my differential equation. In short, I'm writing where alpha is like I can write alpha is some constant which is given by 2m v naught upon h ket square, and k square is some constant which is given by 2m e upon h ket square. Now, if I solve this equation for x not equal to L by 2, this will become 0. So I'm left with d square psi upon dx square plus k square psi is equal to 0. And if I solve this differential equation, I can get oscillatory solutions, either of the form a sine kx or of the form b cos kx. So either you will get this particular solution or this particular solution. Otherwise, you'll not get another solution. Okay. Now, given conditions that your psi is 0 at 0 and psi L is also 0. So if you are given these conditions, so what does it mean? It means that in any case, your b should be equal to 0. Okay, because if you place this condition that your psi is equal to 0, then this particular wave function, like even if I write the linear combination, so if I write the linear combination of it at x equal to 0, so at x equal to 0, this will go to 0. So I remain with b, so b becomes 0. So in any case, in general, I can write my wave function would be of some form a sine kx. Let us see how does that particular. Okay. Now also you can see that there's a Dirac delta potential located at the center. So let us divide this definition into two parts. First part, I can simply write a sine kx from, let's say, x equal to 0 se lagakar you can write till L by 2. Now at L by 2 you may have a difference, like you have to have two conditions. The first condition should be that whatever is written here, like whatever function comes here must have a 0 at L, That is one part. And another thing is, in any case, my function should remain continuous at L by 2. So what I would do, I would simply construct another solution like a sine k, and I would simply write it as L minus x. Why I would do so? Instead of writing kx, I would write L minus x. Why? Because now you place at x, you can place L. So if you place L, this will be L minus L. This is 0. Obviously, psi L is 0. And psi of L by 2, you see, if you place L by 2 here, so it will be L minus L by 2. So overall, it is L by 2. And here also, it is a sine k L by 2. So overall, you can find that this particular wave function would be like continuous at L by 2. And overall, you can see that this particular wave function is 0 at 0, and that's at L also it is 0. So overall, this satisfies your initial boundary condition. So this is how your wave function would be constructed. Is that clear to you till now? Okay. Further, I'm supposed to write the ground state wave function. So I'll just correspond that to k equal to kg, not much difference. So how would it be? It will be like a sine some kg, where kg corresponds to the ground state. And this is how it will be. Okay, so in general, I can write. Now let us find from the solutions. Let us find from the graph that is given how my function would in general be. Is that clear to you till now? हाँ गया सारे बच्चे. भरत समझ में आ रहा है अभी तक?
Yes, sir.
अल्पना को आ रहा है? So इसको अपने काम करते हैं, कॉपी कर लेते हैं.
हेलो सर, नमस्ते सर.
नमस्ते बेटा, बोलो.
सर मैंने अभी ज्वाइन किया है.
ये तो फिजिक्स चल रहा है बाबा. मैथ्स नहीं है आज।
अच्छा मैथ्स नहीं है सर।
हाँ
एग्जाम मेरे तो मैंने फिर नहीं ज्वाइन किया।
हाँ हाँ, कोई दिक्कत नहीं। सो तुम एक काम करो, कॉम्प्लेक्स मैंने पढ़ा दिया है, तुम उसकी एक बार प्लेलिस्ट चेक कर ले। सो उस पे मिल
जी
जाएगा,
सर।
है ना?
ओके सर।
तो ठीक है। सो देखो, सो दिस इज हाउ इट इज। सो देखो साई एक्स इज दिस। इस तरीके से आपका ग्राउंड स्टेट। अब थोड़ा सोचते हैं इसके बारे में। First thing up first is both of these functions are continuous functions. Okay, a sine k kgx and a sine kl, like kgl minus x. Why I'm writing kg? Because that corresponds to the ground state. So kg. So overall, अच्छा एक चीज समझो. If I make the graph of sine, so graph of sine is this way, and if I make the graph of sine square x, so how it will be? It will be just on the positive side with slightly like this way. Okay, is that clear to you? mean समझ पा रहे हो मेरी बात? हाँ? So overall, it will remain between 1 and -1 only, but the negative part will become positive. So this is how your sine square would be. Mostly, मतलब थोड़ा सा एक idea लेके चले. This is how it will be. Is that clear? Now, if I make this graph, if I try to make the graph of psi g x mod ka whole square, so it will be the graph of I think a square sine square kgx for all x lying between L by 0 to L by 2, and from x lying between L by 2 to L, it will be a square, and then it will be sine square. This will be kg L minus x. Okay. Okay. Now, if I make this graph, if I make this graph, अच्छा एक और चीज समझो. If I from the past experience we know that from the problems done before, we know that wherever your Dirac delta potential is located, so जहां पर भी wherever your Dirac delta potential is located, you encounter one encounters a
Pink.
one encounters a discontinuity in the derivative. Discontinuity in the derivative. This is very much clear. Here also you can see that if you try to differentiate this psi, like psi gx. So if you differentiate psi gx, what you will get? So if you differentiate your psi gx for all x lying between L by 2 to 0, so how it will behave? It will be like, I think it will be kg, it will be a cos kgx. And if you differentiate for L by 2 to L, how it will be? It will be minus kg a cos of kg L minus x. Is that clear? Now, if you place x equals to L by 2, if you place L by 2 here, so it becomes L minus L by 2. And if you place L by 2 here, it becomes kg a cos kg L by 2. So on the left, you have kg a cos kg L by 2 on the left, and on the right, so this is your right hand derivative, this is your left hand derivative of the wave function at L by 2, and this is your right hand derivative of the wave function at x equal to L by 2. So here it is like minus kga, and this is cos of kg L by 2. Overall, you can see that your wave function is non-differentiable at L by 2. So obviously it will encounter it will have some kind of cusp. It will have some kind of cusp at x equal to L by 2. Is that clear? Now let us see from, because this is examination question, so kuch hint we'll have to take from the so option number D is quite rejected, because see, you can understand that at x equal to L by 2, your wave function is given by, I think, a sine kg L by 2. Okay, this is clear. And overall, this is also smooth also, so it is not a cusp kind of behavior. So I cannot expect this kind of behavior. So option number D is rejected. If you see option number C says there is a cusp, no doubt, but this particular function is linearly increasing. This particular function is linearly increasing, but we know that for all x less than L by 2, my function is sinusoidal. See, for all x less than L by 2 and even for all x greater than L by 2, my function is sinusoidal. It cannot linearly increase for sure. So option number C is also rejected, because this is a graph which looks like an increasing function from here and then decreasing function from here, and there is a non-differential point. So either it will be option number B and option number A. Okay. Option number B also has a smooth point here, so it cannot be the case. It cannot be the case because this is not a cusp kind of behavior. This is a smooth behavior. Are you getting my point? So this is a smooth behavior, but this particular behavior suggests that this may be the case. Let us see if that's the possibility. So a tentative graph or whatever limited information is given, what you can do is you can try to make a plot. So you already know that your at x equal to L by 2, your function is continuous. So there will be a graph of sine. So how does sine grow? Sine grows, and at L by 2 it will come this point, and at L by 2 again it will start from this point because it is continuous. But see, here the derivative and here derivative must differ. So derivatives are differing, so there would be a cusp at this point, and this is how your psi x versus x would be. So there is a cusp here. Here is a cusp here. Okay. Further, if you take a modulus square also, the graph will remain the same. The overall change would be in the amplitudes. Overall, the graph would look the same. But overall, you have to understand that it cannot be smooth here. It has to be a double point. So it has to be cusp here. So I hope it is clear. Is that clear or is that not clear?
सर जो आपने ऊपर बताया जहाँ पे x is not equal to L by 2 है,
हाँ जी, बोलो बोलो क्या कह रहे हो?
सर आपने एक जगह एक सेक्शन में लिखा था ना x is not equal to L by 2 पे सॉल्व किया था
हाँ हाँ हाँ.
हमने.
Yes. Yes. So if x is not equal to L by 2, this will be 0. And this is d square psi upon d square plus k square psi. And the k square is 2me upon h kt square.
Yes,
See,
sir.
now you are in one-dimensional potential well. In one-dimensional potential well, what happens? The particle remains bound in one-dimensional potential well, and because your potential is infinite outside, so it does not. Although there's a possibility of tunneling, but overall, particle it is said that it is confined. Question itself says that your particle is confined in one-dimensional potential well. So I'm discussing only this case. So now you know that whenever it is in the one-dimensional potential well, your energy eigenstates are n square, pi square, h square upon 12 is ml square. So they're positive. Okay, so yesterday we were discussing attracted Dirac delta potential, where we were studying that if at all there is a possibility that particle gets trapped or particle gets trapped into that particular potential well, then the energy should be negative. But here you know that if a particle is in one-dimensional potential well, the energy is positive. So E is positive here, so I don't have to write minus minus and then we do something of that sort. So the solution remains sinusoidal here also. Is that clear?
Sir, we could have constructed solutions of the exponential forms also, no? Or not?
But then how would I would say that it will remain bound? I mean,
It will how it will remain bound.
See, नहीं देखो मेरी बात समझो. Bound मतलब एक मेरी बात समझो. What I am trying to say is, if I am in a one-dimensional, देखो initial problem statement says that a particle is confined to one-dimensional potential box of length. ठीक है? If a vanishingly thin but strong repulsive partition is introduced at exact center, so initially your particle was in a one-dimensional potential. So whenever we discuss one-dimensional potential well, your energy E is positive, isn't it? Your energy E is positive.
Yes, sir.
Okay, and your V is 0. Your V is 0. So this is how it is. Now there is a sudden modification in the energy, and that also repulsive, not attractive. That also repulsive. So if at all I would write, I would say that my energy E is positive here. So if my energy E is positive, why should I write negative and negative? So basically, what I know what doubt you are raising, probably you are raising that why not I'm writing negative E here as I wrote in the other cases. So other cases were discussing an attractive Dirac delta potential. Whenever you have an attractive Dirac delta potential, the overall energy, whenever you encounter an attractive potential. So for example, gravitational potential. So gravitational potential is an attractive potential. You just find the total energy. Total energy always remains negative. For the attractive potentials, you find, say for example, gravitation itself. So you just find minus g m upon r, and you just find plus kinetic energy if you raise. Even if you find atomic systems where you just take Coulombic kind of model, like Niels Bohr model, that you say that an electron is confined inside an atom and it revolves around the nucleus in its stationary states. So whatever energy you get negative. So whenever you have the cases of attractive potentials, the total energy remains negative. But here you see you are inside a potential well, and that particular potential well, you already know that your energy remains positive, and further you are encountering a repulsive potential. So overall energy would remain positive only. So I cannot expect, I believe, as much as I know, I cannot expect a exponential kind of behavior here. Is that clear?
सर
Or
अगर यहाँ पे सर यहाँ पे अगर हम अट्रैक्टिव लेते तो कुछ चेंज आता?
क्या लेते, सॉरी?
अट्रैक्टिव पोटेंशियल लेते जो पार्टीशन
अट्रैक्टिव,
क्रिएट
हाँ,
किया है वो।
बिल्कुल बिल्कुल चेंज आता। अट्रैक्टिव पोटेंशियल लेते तो अलग हो जाती है। Then we would have probably written, then we would have to think about this energies also, like uh, overall energy negative kaise ho, and things would certainly would have changed. This is what I feel. I mean, I don't know much about it because the solutions is not given anywhere, but overall, if I whatever I can comprehend out of it, I'm explaining. समझ पा रहे हो मैं क्या कहने की कोशिश कर रहा हूँ till now?
हाँ जी सर, मैं आपका सोल्यूशन समझ गया, बस मेरे को बस ये डाउट था कि हम एक्सपोनेंशियल सॉल्यूशंस बस अट्रैक्टिव उसमें ही लेंगे क्या? क्योंकि साइन और कॉस भी तो लास्ट में एक्सपोनेंशियल ही है ना सब।
Right. But then they're periodic also. Like in any case, exponential, what should I say? They are periodic as in matlab they will remain, this particular particle is confined in this particular space, isn't it? So if I take an exponential case here, so how would, well, I'm not able to explain that, how would periodicity be remain intact? I have to see that my particle in any case remains between 0 and L. So I have to have some bound kind of wave function. That is one solution that I can say. Overall, I'll try to get back to your problem also. But overall, are you getting my point till now? This is what I have made just out of this particular problem. Because otherwise, we'll not be able to do this. I mean, is that clear?
Yes,
Because
yes,
see,
sir.
whatever you say is also right. But whatever you say is right, then this may be also a solution. Because this looks like exponential.
Yes, sir.
Are you getting my point? So this looks like an exponential. So it is like e power minus modulus of x. Whatever we are getting in e power minus modulus of x is what we were getting in attractive Dirac delta potential, isn't it? So
यस सर, बट सर ये साई वो है प्रोबेबिलिटी डेंसिटी है ना,
this
साई
is probability
स्क्वायर है
density.
ये।
This is probability
तो
density.
हमारा तो ये साई एक्स आया था ना सब कुछ।
Okay. So देखो होगा क्या? Even if you take psi like modulus का square, even if you take that also ना, तो देखो psi mod का square अगर तुम differentiate करोगे भी, let's say psi x का square, because real wave function है तो मैं ज्यादा mod नहीं लगा रहा हूँ। अगर ये इसको differentiate करोगे तो क्या आएगा? 2 times psi x, and then it will be accompanied by psi dash x. So if your psi dash x is differentiable at some point, your psi x का whole square will also be differentiable at that. Is that
यस
clear?
सर।
If I'm saying my psi x is non-differentiable, or it is encountering a cusp at x equal to L by 2, then certainly that behavior I can expect for psi x ka mod ka whole square as well. So this is what is one tentative sort of graph, one little bit, because there is not much information given about kg also. How can I extract kg also? That is also not given in the question. So overall, I will have to restrict myself to this particular point. Probably एक दो चीज हम देख सकते हैं अगर if I use my equation number 3, then I may think about that also. So let us do that also. But overall, I hope it is clear.
यस सर।
Okay, now let's say you already. Achha, what do you think about? I should ask you this question instantly. What do you think about? What do you think about the energy states? So even like energy state, only ground state we are considering now. So even if we are considering the ground state, now will the ground state get elevated or will it become less as compared to the one-dimensional potential well? If I compare my now new ground states with respect to if I compare it with one-dimensional infinite potential wells, will my energy get elevated or not? So if I compare my new energy states or new ground state energy, will it get elevated or will it get lesser compared to one-dimensional infinite potential well. So if my one-dimensional infinite potential well, the ground state is given by, I think, n square. Sorry, this is pi square h ket square upon twice ml square. Is that clear? Now, after reducing a attractive Dirac delta potential, a repulsive Dirac delta potential at the center, if I consider a repulsive Dirac delta potential at the center, now how would my energy states be? Will it raise? Will it get lesser? Should we think upon this? Probably this is not asked in the examination. I'm just giving you a hint. So that probably if that question comes in the examination, then how to solve that particular problem. So,
yes,
like for that, you just try to solve. अगर हम लोग इसको देखें, let's say, if we try to solve, because this was the expression that we've not used till now, right? And this will give us the value of k. And if we get the value of k somehow, we can get the value of energy. So this equation is left undone, like it is not done till now. So let us do this particular. And I've got your question also. So let me think about it and I'll respond to that particular also. Can we not take exponentials also? So that I would think, okay? Because this is what I can take, because repulsive potentials, I only expect energy to be positive and already energy is positive. So I did not think that way. I will think that way and I'll explain if I will be able to explain. Okay. Now, if at all, if I use this particular equation, that is your d psi by dx at L by 2 plus epsilon minus d psi by dx, and at L by 2 minus epsilon if I take, and this is, I think, equals to, it should be equal to what? It is equal to 2m v naught h ket square psi L by 2m v naught. So it will be equals to 2m v naught upon h ket square psi f L by 2. Is that clear? Now, if you try to solve this particular this thing, I know that for x psi greater than L by 2, my expression is a sine k L minus x. So if you differentiate it, what you will get, if you write even the ground state, minus kg a cos kg L minus x. Is that clear? So I will write minus kg a cos, and if I place L by 2 plus epsilon, given condition epsilon tends to 0, it will be L by 2. And again, this will be minus kg a cos of L by 2, kg L by 2. Is that clear? And what will be psi of L by 2? We know that it equals to a sine kg L by 2. Overall, this is the case. Okay. Now, if I just try to solve this equation, probably I may get some solution. And remember, kg corresponds to energy solutions, which are ground state energy solution, because kg per square was, I think it was 2meg upon h ket square. So the solution of kg would correspond to the solutions for the ground state. Okay. Now, if I just take this this thing, I think a will get cancelled. So a gets cancelled. Forget about it. This cos kg will become, I think, cot kg. So it will become, I think, cot kg L by 2 would become, I think, minus. So this 2 will also get cancelled. Minus mv naught upon, I think, kg h ket square. Is that clear? So this will become minus mv naught upon kg h ket square cot kg L by 2. Is that clear?
Yes,
okay.
sir.
And probably what we can do is we can multiply this with L by 2 multiply. So this will be, I think, cot. And if you take kg L by 2 as one expression, that is, let's say we take it as q. So this will be cot q is equals to minus of mv naught. इसको भूल जाओ, इसको कुछ constant बोल दो, alpha divided by q, है ना, ऐसा कुछ. So it will be minus alpha divided by q. Is that clear? And
Yes,
you just make the graph. You just make the graph. So we know that your cotangent graph starts, this graph cot is, I think, infinite at 0, and it is 0.
So 10 का ही बना लेते हैं.
हाँ, 10 का बना लो, cot का बना लेता हूँ मैं, cot लिख देता हूँ.
ठीक है.
हाँ, वैसे cot का बनाने में एक फायदा ये था, tan बनाने में एक फायदा ये था कि तुम्हारा ये, हाँ ठीक है, that would be good. that tan का बनाने में ये अच्छी चीज हो जाएगी. So if I make the graph of tan Q will be negative of this. अच्छा एक आइडिया ले लेते हैं पहले ही, देखो एक आइडिया लग रहा है, इससे ही ले लेते हैं एक आइडिया एंड देन वील मेक द ग्राफ। इससे एक आइडिया लेते हैं कि इससे ही पता लग रहा है कि kgl/2, देखो ये नेगेटिव है, like cot kgl/2 this is negative, and understand that cot is positive at first quadrant, cot is negative in the second quadrant, cot is positive in the third quadrant, and cot is again negative in the fourth quadrant. So in any case kgl/2 will either lie between pi and 2, pi and pi/2, matlab if at all the solution would exist, it would exist if kgl/2 lies between this or 3 pi/2, let's say 2 pi. But you already know that we are talking of ground state energy, so we'll be talking of minimum energy. So if kg is lying between 3 pi/2 and 2 pi, obviously it will generate a greater energy value. So obviously this will not come into place. So we can expect a solution between pi/2 and pi. Is that clear?
Yes, sir.
We can expect a solution from pi/2 to pi. So for ground state energy, you can see the range of kgl/2 must lie between pi/2 and pi. Is that clear? Pi/2 and pi. So my kgl/2 should lie between pi/2 and pi. And if I try to just think about, this says that your kg must be greater than, I think, pi over L. Is that clear? Now, if I want to write my new energy, so my new energy, it would be equals to what? Pi square kg ka square upon twice ml square. Is that clear? And since kg is greater than pi/2, that implies kg ka square will be greater than equal to, there is some mistake of what? I think this will be, kg will be greater than, I think, pi over L, not pi over, sorry, pi over L. This is pi over L. So if kg is greater than pi over L, then kg ka square will be greater than pi square upon L square. So it will be greater than, there is some mistake. This is h cat square, no? This is h cat square, then it will be greater than pi square. Again, there is L ki power 4. I don't get it. Kahan se galti hui again? What was that? Sorry. एक मिनट देखते हैं वापस से. अच्छा, this is kg का square is 2m eg upon h cat square. So eg is h cat square kg square upon twice m. It's not even L square. Sorry. So it is just twice m here. My mistake. So it is just twice m here. So you can expect that your new energy ground state, new ground state energy will be h cat square kg square upon twice m, and your kg is greater than equal to pi upon m. This is what you got from the third equation, like Schrodinger equation of the modified potential, right? So while solving the Schrodinger equation for the modified potential, we got the range of kgl/2 greater than pi/2 and less than pi. So overall, you can expect that this is greater. This new energy ground state is greater than pi square h cat square upon twice ml square. So I can say my new energy ground state is greater than the energy of the ground state of the one-dimensional infinite potential. So overall, your energy will become greater than the initial energy, and that is we were expecting also, because now we are not no longer putting an attractive potential, we are putting a repulsive potential. So overall, it will add upon the energy. So the ground state energy will get elevated. Is that clear? The ground state wave function has got changed, and the ground state energy also, the new ground state energy would also get elevated. So there are two observations. The first observation you can see is that your ground state energy, the wave function of the ground state is discontinuous. The psi dash is discontinuous at L/2. This is first. Second, your new ground state energy is greater than the original one. Original one, I mean the one which has one of the infinite one-dimensional potential. Okay, is that clear? And this particular thing also I'll solve. But overall, I've got this topic. So I know that, so even if I don't make a graph, even if I make the graph, I'll get solution only in this region, that is pi/2 to pi. That I will see also. Okay. And एक और चीज समझो, if my V0 tends to tends to infinity, if my V naught tends to infinity, because we know that this, if it goes infinity, it implies what? It implies this particular thing is going towards what? Pi. I know that cot pi is minus infinity. So if V naught goes towards infinite, so if I make the amplitude of the attracted director potential as large as possible, overall it will go towards infinity, overall it will go towards minus infinity. And I already know that my cot pi is minus infinite. So as V naught tends to infinity, I can say that my kg will tend towards, this kg L by 2 would tend towards pi, and that implies your kg would tend towards 2 pi upon L. So I wrote ना कि जो kg की values होंगी, it will lie between L upon pi to 2 pi upon L. So kg will tend towards 2 pi upon L only if your V naught tends to infinity. So overall kg will lie between this and this. And overall, if your this Dirac delta potential, the amplitude of the Dirac delta potential tends towards infinity, only in that case your kg tends to 2 pi. So I will give you this as a homework, that you just find that these solutions from graph also. So I think the graph also would give you tan q you already know, q you already know, but you have to take now negative q. So you have to take a slope which is negative, and pass. And this
Yes.
particular will be passing through origin. So I think this is only the solution that we get. I hope it is clear.
सर इसमें जो ये अपना डायरेक्ट डेल्टा पोटेंशियल है, इसको हम परटर्बिंग पोटेंशियल कंसीडर कर सकते हैं क्या
बिल्कुल कर
इस
सकते
सिस्टम में?
हैं, बिल्कुल कर
तो
सकते
उससे भी निकाल सकते हैं हम एनर्जी?
हैं, उससे भी निकाल सकते हैं. That we'll do in perturbation also.
यस सर.
Okay. So overall, अच्छा, find new energy also in this case. So I think this will be 4 times the original energy that you just find. Okay, this is your homework.